Hello community, so great that you are back. Let's talk about the latest in AI research. HyperGraphRAG combination with reinforcement learning. Now you know the classical GRAPHRAG, my goodness, I have so many videos on this here from a graph neural network, scaling GRAPHRAG, beyond GRAPHRAG, and then we had LightRAG and PathRAG and all the variations. But today we need some new tool, we need a HyperGraphRAG system. And this was done here by Beijing University at the end of May 2025. You have your GitHub repo, you have here the complete code, you have everything available for you if you want to try it out. And here you have now the standard RAG system, the classical GRAPHRAG system, and now our brand new HyperGraphRAG system. And you immediately see we operate here with a hypergraph structure that you know from mathematics and theoretical physics. So let's have a look. If you want to compare here the knowledge construction and the knowledge retrieval process for the standard RAG, the GRAPHRAG, the LightRAG, the PathRAG, the HyperRAG, and the brand new HyperGraphRAG system, here you have it here, one view, you see exactly what is the difference. And if you want to have a definition of a hypergraph, yes, of course, easy. Each hyperedge connects two or more entities. This is it. Now, this was based on a publication also here by Beijing University here, and they had here hyper-relational knowledge graph. This was by May 2023, and they simply here developed here this methodology further, and we have dual attention layers and self-attention layers for local level attention. I hope you're familiar with this. Simple example, you have a person, this is a function, the position held, and you have so much more information to this single person. You have so many others like start time replaces, the end time replaced by. So all this information you want to have now in a higher dimensional complexity instead of your simple GRAPHRAG system. So what we do? We have, of course, domain knowledge. Normally we have it in PDF, in books, whatever, on the internet. So we have tons and tons of pages. So we extract everything into a hyperedge structure. And you see here, beautiful, give you here this particular example. And we have now, if you want, a hypergraph. The knowledge hypergraph is constructed automatically. Just have a look at the GitHub. It is done completely autonomous. And I will go through the process how this is happening in detail in about 2 minutes time. The beauty is suddenly over our hyper edges. We have now, if you want, a clustered multidimensional added content. So therefore our RAG extraction will become much more efficient. So let's talk about this. This is now my third video in a mini series that I have about how can we really go to the leading and bleeding edge of AI research. In my first video, we talked about Search R1, training the LLM to reason and leverage a search engine as a tool with reinforcement learning, MCP. The second was unifying a RAG system, a classical RAG system, and the reasoning, the deep reasoning through a reinforcement learning. And today we talk here about the next step in the complexity. We talk about Graph-R1 from the end of July 2025, Agentic GRAPHRAG framework via an end-to-end reinforcement learning. Human, completely out of the loop. Here you have an AI system that tries to self-learn, self-improve, self-reason on multiple levels of complexity. Absolutely fascinating. Now, the idea here from Graph-R1 is simple. No? You know, R1 here, we have here the GRPO optimization methodology, and graph, you have understood it right now. We go now with a hypergraph, a knowledge hypergraph. So therefore, you see, this is now the third video in this series, and now it is so easy to understand what is happening. So you have here your agent, ask me anything, I'll reason through the knowledge hypergraph to find the answer. You have a multi-turn interaction, not just a single-turn interaction here, given that you have so much information on a knowledge hypergraph. And then let's say the user has a simple task. Hey, who is the spouse of the director of the film in memory of Sergio somebody? So you see, you need more than one simple run here to a RAG system because you have here multiple links. And the agent now thinks, hey, to answer this, I need to find out who directed the film and then find out who is the director's spouse. So you see, simple query, knowledge hypergraph. director of the film in memory of Sergio. And now it is so much easier because you have a higher dimensional complexity on your graph structure with hypergraphs. And so every piece of information adds on, and finally you have the perfect answer. Let's have a look at this also in GitHub. Everything is already available for you. They have here different data sets that they had already transformed to a Parquet format and then for a knowledge hypergraph. I will explain in a second how you build your knowledge hypergraph. It's rather easy. It's completely automated. You have here the Python code already. You can set up a port and run it immediately. But let's just start to understand what is the difference here to the classical GRAPHRAG pipeline. And remember, in my videos about GRAPHRAG, I showed you the knowledge graph construction was stage 1. Then we had the graph retrieval. This was formulated as a two-step process. We retrieve here the candidate reasoning paths. And of course, we had to prune here the irrelevant out. And we had here a beautiful optimization. Plus the answer generation was then simply given the human query and all the selected path. The answer generation produces here a natural language answer. Why? Grounded in the graph-based evidence. And I explained the formula to you already. Now, if we go now to a hypergraph retrieval, you guess what? It is almost identical. You just have now a dual path interaction process for the hypergraph retrieval. You also have the entity-based retrieval and the direct hyper-edge retrieval. Remember, this is here where we have an added complexity. But you see, nothing else. Directly retrieve the hyper-edges based on the query hyper-edge similarity. More about this in a minute. And collect their associated relational facts. You just have a lot of more information if you just compare this to a single node representation and a single multidimensional edge representation. And then you fuse everything back together via a reciprocal rank aggregation. Great. So here you have it. This is here, if you want, 1, 2, 3 steps here of the classical GRAPHRAG pipeline. And here you have your 1, 2, 3 steps of your hypergraph pipeline. And I just wanted to show you, it is so easy, it is so similar. You just have to integrate here the higher complexity that provides more information. Now, you know, in my video where we talked here, this is here the thumbnail, and here at 8 minutes 52 seconds, I showed you here the GRPO objective, the object that we are doing here a mathematical optimization process on, and I explained here all the different terms to you. If this was here the GRPO objective and the search R1 template, now I show you the same for the Graph-R1. So the Graph-R1 template you have here, and you will immediately see, oh, it's so similar, almost identical. Yes, of course, because we just exchanged now that we have somewhere a search on the internet with a search here on a structured hypergraphs. And you're not going to believe it here, our objective here, also going with R1 GRPO methodology, is simply this term. Is there something special? Yes, we have here a row parameter for adjustments for the distribution shift we're going to expect. And our advantage A that you know, that you're familiar with, we normalizes here the reward using here a particular scaling function f. Never mind, it's a technical detail. But you see, you're immediately familiar. We have a Kuber-Klaber divergence, our beta parameter, our clipping that is happening. This is everything that we know, that we understand how it works. Now, what is different? And now, careful, now the reward function. And you remember in this video I told you, the authors of Search R1 told us, hey, we use the simplest rule-based reward system that we can find with a final outcome reward function. And they said, yeah, in the future we will go to more advanced reward function, adaptive retrieval strategy, multi-tool integration, and so. But now here in this new one, they really went this extra mile, and have a look at this. So they decided now, different to Search R1 in Graph-R1, to go now here also with an outcome-directed reward function, but we have here 2 parts. At first, and this is what you're already familiar with, a format reward. So it simply encourages here our AI agent to follow here the intended reasoning structure. So if the output includes here a well-formed block that you have defined, and then the second one, we have the answer reward. So here we measure really the semantic correctness of the answer generated if we compare this now to the golden ground truth answer. So again, a process that we know, but now a little bit more complicated. And you say, hey, wait, I know the I operator here. Yes, of course, this is exactly that I showed you here when we have the loss masking in Search R1. You see, it is so easy if you have a 3-part video series. Now you just see this and you immediately understand what's happening if you have seen the other videos. But you say, hey, wait, there was the second video, no, where we talked here about RAG 3 in reinforcement learning. And this UR2, as I called it, if we looked at their reward ideas at 17 minutes and 34 seconds, you also remember, no, we had a 2-stage idea for the reward function. The same, we had a retrieval activation, where the reward function only cared about the correct tool use. And the answer, the correctness was ignored in the first step, and then only in stage 2, we went here for further optimization for the answer quality. So we evaluated the correctness of the final answer here in UR2. And you see that this idea from UR2, from the authors of UR2, you find now also here in this publication, here in the third video, where we also have here the format reward function and the answer reward function, where here in the second time, we go for the semantic correctness of the generated answer. So you see so many parallel things here. This was by Tsinghua University. Great. So what are the insights now in our third video of this mini-series? And I thought I will frame it now differently. And up until now, I only thought, hey, we have to improve the performance of the agent, of the AI agent. We have to improve here all the memory optimization, key value cache optimization, and so on, MCP optimization, everything about the AI agent, the LLM in itself. And now here I see, brutally I see, it is also about the structure of the environment. Because the agent interacts, now this is the definition of an agent, yeah, with the environment. And how this environment is structured, the complexity the AI agent encounters now in the environment is a defining factor for the performance of the agent. And I think one of the reasons for the Graph-R1 success, and I'll give you the performance data in a second, it shows us that this structuring the knowledge here of the environment is not just a data engineering task that we just clean it up here. No, this is a fundamental part of building here a high-performance reasoning agent. So, short, no longer about just building smarter agents, because the agents interact with something, and we have to look at this as a complete system. No? It's a kind of a symbiotic system where you have the agent and its knowledge environment. If you go with a hyper knowledge graph, those systems have to co-evolve in their abilities when they improve their performance. Okay, so one of my next videos will be something like this, from an unstructured chaos here in the external world to a semantic order. The environment as a catalyst for advanced reasoning of multi-agent system, because we have to rebuild for an optimized representation of the environment given our current AI system. And talking about current AI system, just yesterday, I found this video here on the internet. Here's all that you can find it yourself. What was the main topic? They crash tested here the performance of a lot of AI-enabled cars. This is here from China, but absolutely fascinating to see in the night on a highway, high speed, and you have suddenly here a car standing, but not with the front or really the side, kind of a diagonal interpretation. No? And it is, if you see the title, you understand exactly what happened there. And interestingly, one of the commentators noticed that at higher speed, at a highway speed, maybe those AI system, if you have so many sensors and lidars and whatever and laser and on, maybe it is too complicated, the fast-changing environment with a highway speed for our current AI systems that are built into our cars, not just to detect and analyze the complete environment, understand the positioning of the objects in the environment, understand everything about the dynamics of the objects, and then try to calculate here an escape path, an escape route, that you are not crashing into this obstacle. And absolutely interesting, if you see this in real time, so thank you here to the Chinese, I don't know, TV or broadcasting station, ADAS test, great. This was absolutely fascinating to see those AI systems in real time and how they fail, massively fail. And the more systems they have on board, there was a correlation to a failure rate. And I had to think about this. There was one car, a really cheap one, not a lot of sensor, the cheap version. And this car managed to solve a lot of problems. So you see, the more sensor arrays you pack into one system, you have, tons of data streams coming in at hyper speed to have here the speed currently. With our current implementation, it clearly shows us here the limitations of our AI systems. Summary. The real world is filled with so much complex facts, especially at hyperspeed, that connect to more than two entities. So if we go with just a classical graph structure, it will not be enough. And I have here this sentence here. This is here from the graph paper here, the R1 paper. Look at this sentence. You have a relation between a patient with a particular condition, hypertensive, with a specific level of an object, with a specific quantification and a specific diagnosed grade. Now, if you want to map this here to a classical graph structure, you will miss out something. You will miss out on the interconnected complexity, on the interrelation of those facts. Yeah, standard RAG, you just have chunks. Standard graph, of course, you have here breaks down into a series of lossy, incomplete pairs like those. And it really takes here kind of a HyperGraphRAG, this hyper edge idea that you really have here if you want a grouping, a clustering here, or that you have all the nodes that are specific to this specific patients, and we have immediately access to this information. So I think the idea here of a hyper edge could really be the jump forward that we need. Because this hyper edge here links all four entity nodes here of this single sentence together. So now we have here how we do it. And now we just have to understand what is now the exact flow of this operation before we let reinforcement learning just automatically learn it. That the AI system learns this automatically. So therefore we have to have now the non-RL version where we really define in absolute precision the flow, what RL will learn in the next step. So the mechanics of how to use now the hypergraph in detail. 4 points. At first we have to have the knowledge hypergraph construction. You have the code for this. Imagine you take Wikipedia, here the text of Wikipedia, and you tell, your Google or your Microsoft, and you say now, okay, now please build me a hypergraph from all of Wikipedia, of the global Wikipedia. Really interesting if we would have this data for free for developers. Second, we have a dual path retrieval strategy, as I already showed you. Much more than a simple keyword search. We have a two-pronged attack. We have the entity retrieval and the hyper-edge retrieval. Plus, then we have the hypergraph knowledge fusion. Remember, this is the critical step. It takes the retrieved entities and expand its search to find all connected hyper-edges. But it also takes the retrieved hyper-edges and expands those hyper-edges to find all connected entities, all nodes that are within the hyper-edge. No? So you have a bidirectional expansion, like the Big Bang of the universe. You ensure that it has the full data content or full information content here for everything that is even close by. And then you have the generation. Then you have the hypergraph guided generation, your classical RAG system here. So the final retrieved knowledge here is, you can combine it with whatever other system you like a traditional text chunks, and you fed this into an LLM with a specific prompt, and then you have your classical RAG system again. Did you notice something? I was very fast here because at point 2, the hyper-edge retrieval, in parallel, it finds hyper-edges. that are semantically similar to the user query. And I saw this is not possible. So going back to this point, 2, the authors really decided that they have to build a vector space, in addition a vector space, for an embedding. So for the process of find similar expressions like to the human query, they still go with a vector space. We have so many other opportunities, but okay, they go with a vector space and they say, listen, we have a separate sentence embedding model. They use anything right out of the shelf, never mind. And they create now a vector space representation and embedding for every node and for every hyperedge. So exactly as you would do for the classical RAG system. And why? Because, of course, also for the Graph-R1 agent that we just built, we have to find here a semantic similarity search optimization. So we have to go through this cosine similarity function. And now the question is, what are the elements in this cosine? What is the complexity of the mathematical space? And in the simplest case, it is a vector space. But of course, you would like to operate with a Hilbert space. I know this, but for the moment, we have to go with a vector space. Okay, so just that you know, we also have to build a vector space and embeddings, and then we have a semantic similarity search, classic. So now we have everything. Now everything is understood. We understood the process, we understand the steps, we understand the flow, the complete flow that is happening. And now we just tell the AI, hey, buddy, you know how to do reinforcement learning, yeah? This is your data set, this is your methodology, this is your flow. Learn. You see? Great. That's it. So therefore, the hypergraph construction method in the HyperGraphRAG system is exactly the one we used in the pre-processing here of Graph-R1, nothing different. The multi-stage retrieval and diffusion pipeline in HyperGraphRAG is exactly the process that we need for the Graph-R1 agent. And we just use here the classical reinforcement learning with GRPO. I showed you already here the objective function to learn the system and let it perform autonomously its optimization process. That's it. So, and the beauty is, instead of a fixed human-coded, hard-coded, the number of loops, the number of the level and whatever, pre-programmed retrieval strategies, now we have a more complex mathematical optimization process where the Graph-R1 agent learns on its own its optimal multi-turn policy to find a solution to the human query. I want to show you the prompts that they used in the HyperGraphRAG system because I was really interested myself and I said, how complex will this be? Guess what? It is again another LLM, another AI system. The human is not anymore in the loop. So the relation extraction prompt, T is missing. Yes, this is a screenshot from the document. So this prompt is designed for extracting here a structured, not a binary graph relational facts, but an n-ary relational facts, a hyperedge from raw text documents. This is done here with this, and some LLM is performing the job for this. Then, of course, we need an entity extraction prompt. Now I have the T. Congratulations. So this prompt, this is the prompt. Of course, we have here examples filled in on real data and the query that we really have. This prompt is used to extract here the key entities from a user query. That we understand, I've given you the sentence here, no, the medicament, and this is a person with a precondition, and there's a quantifier, and then there's also something. So we extract here our entities, and then here the retrieval augmented generation prompt. Everything that you're familiar with, I just showed you the template before. Now you have here the complete prompt structure. This is it. So nothing special, nothing fancy. Just we go to a more or less a HyperGraphRAG system and we combine it in an intelligent way with a new optimized reinforcement learning methodology. What are the results? Is it any good? In the annex of the Graph-R1 paper, you find table 5, and I highly recommend this because here, let's start here. You have the query, you have here a very particular medical question, and then you have the golden correct answer, the human answer, ultrasound, whatever. And then we have here a lot of benchmark here, test here, different perspectives here of the machine. So let's have a look. Yeah, you see we have here standard RAG, GRAPHRAG, LightRAG, PathRAG, HyperRAG, and the HyperRAG. But that I can read it, I found here this. So let's look at the first three. Naive, great. Standard RAG, you have here the scoring for each of the benchmark. And then the GRAPHRAG here with the evaluation scoring. And you get a first impression where we are with the benchmarks. Then we have LightRAG, PathRAG, HyperRAG. And then here, finally, the evaluation score. And you see, the first one is 100%, 70%, 92%, 90%, 95%, 100%, 100%. So on this selected paper by the authors of Graph-R1, for the complexity chosen by the authors of Graph-R1, this is the result that the authors of Graph-R1 want to show us as the best perfect case for the new methodology. Absolutely fascinating, but you might say, yeah, but how dependent is this here on the specific LLM that you use? And they checked this out. So if they used here a GPT-4 Omni, they used a Q1 2.5, a 1.5b, a 3b, and a 7b instruct. And then you have for all the different data sets, the wiki data set, the hotbot, question and answer, music, and error. And you have here all the parameters now. And you see here again for standard RAG, GRAPHRAG, LightRAG, PathRAG, HyperRAG, and HyperGraphRAG, all the performance data. Just look here at the very last block if you want. A 7b is already a model I would kind of recommend here. Unfortunately, still the 2.5 Q1 and not the version 3 Q1. Never mind. Compared in the methodology, you see that Graph-R1, bold is the best, is really outperforming all other methodologies. Real nice result, but this is, of course, something that we kind of expected. No? So even if you go with the classical data sets here for evaluation, this really looks absolutely interesting for the future. And there you have it. Was simple, no? This is the end of video 3. What we achieved today, we had a RAG system, not the classical RAG system, not the classical GRAPHRAG system, but we went with a higher complexity HyperGraphRAG system, which we need, which is vital for complex reasoning. We defined here all the elements, all the interaction, all the dependencies. We defined the flow of the process. And then we just used here the normal reinforcement learning process with a GRPO objective and some control parameter. And we had here an autonomous, fully automated scaling self-learning optimization problem that the AI could solve. And I showed you the performance of the new system compared to the classical RAG systems. I hope you enjoyed it. Would be great to see you in my next video.